Hi again, everyone. This is the first recording for week 3. And the topic for week 3 is, as you can see here, auctions. So we're going to talk about auction design, but also auction analysis. So you could say using the theory that we learned about Bayesian games and the solution concept, so Bayesian equilibrium, and such to analyze certain auction types. But in this first recording, we're going to talk about auction design. So we're going to look at a very general problem in which auctions actually help you to solve or resolve the problem, the economic problem that we're facing. And so first I'm going to give you the economic setting that we are studying, and then explain a little bit what is the general auction format that solves this problem, which is the VCG mechanism. And then explain how you can, what kind of solution concept we're using there to analyze that specific auction type. But let's start at the beginning, namely with the economic problem that we are actually trying to solve. So the setting is very general. We have a finite set of agents, 1 up to n. So that is the same as what we've seen before. But the setting here is very, very general. So the only other thing that we require to have is a set A of allocations. And that can basically be anything, right? So the only thing that we need to know is how, what kind of goods we have and how we could assign them to different agents. So it can be indivisible items or divisible items or even production capabilities. You can think of many situations that would fit into this very, very general description. The only thing that we do need is that each agent knows how he would or she would evaluate that specific allocation. So you have an allocation A and A. So we have a certain allocation A and A, and then each agent is required to know how he would evaluate that specific way of allocating by assigning a value to it. So that's the VI of A. And remember that A can be an assignment to all the agents, right? Not just to agent I, but so you can also, for example, include that your valuation is affected by what other people would get, right? So we do allow for that. But what is true is that you should know exactly what it is. So there's no uncertainty about the valuation. Each agent knows exactly how he or she would evaluate every specific possible allocation. And the interpretation is like stated over here. Agent I derives utility VI of A from allocation A. And we assume private information, which means that each agent only knows his own VI, so his own valuation function, you could say, but not that of others. So he does not know how other people would evaluate it. And specifically the social planner, so there is also supposed to be a social planner, does not know any of these valuation functions. And so that is one thing. And what are we now supposed to do? Well, what we are supposed to do is to maximize what is called welfare. And how do we measure that? Well, we measure that in this specific case by summing up all the valuations of all the agents. So you have an allocation A, and then each agent has a VI of A, and the total welfare is simply the sum over all these valuations. It's called TU maximization. So you're looking for an allocation that maximizes this specific expression. So the total utility of A, or total valuation of A, is the sum over all the VI of A's. And an allocation is a total utility maximizer if it maximizes this particular expression. So the TU of A is bigger or equal to the TU of any other B. In A, it should say here instead of B. It's a typo. It should be an A over here, of course. Okay. So this is what we want to achieve. We want to find an allocation that maximizes total utility. And of course, as before, if you would have all the information, that would be a simple thing to do. Well, at least you need to do some calculations, but at least it's clear that how you should set about to find such a total utility maximizer. However, the problem is that nobody has all the information to execute this maximization, so to solve this maximization problem. So the question is, can you now build something, a market or an auction or some other kind of trading protocol in such a way that in equilibrium, in that mechanism, so in that specific market or trading platform, you actually achieve this type of efficiency. Like I said, so we have information asymmetries, and we're going to use auctions to solve this one. Of course, like I said, we can also think of many other market designs or trading platforms to solve this problem, but we are going to use auctions. Before we do that, there is one assumption here. So those are the informational assumptions, but there's another assumption on because we're going to use money in this system to compensate each other. But in order to include money in our model, we need something that's called quasi-linear utility. So what does it mean? It means that, like it says here, so you need the monetary payments. And what it means is that each agent not only has a utility for the allocation that of the physical goods that we're going to assign, but he also has a utility for money. And so that is then represented by this UI, and it's supposed to be quasi-linear. What does it mean? It means that if you have an allocation, A and A, and you have a certain amount of money, M, so this is supposed to be a real number, so it can be any number, then the utility for the combination of A with that M is going to be the VI of A, sorry, VI of A plus the amount of money M. So you simply add the amount of money linearly to your utility. So that's what's called quasi-linear. It's linear in money, although it need not be linear in A, if it can be linear in A. So maybe it can't, right? But at least it should be linear in the amount of money that you own. That means that, of course, if you make payments, that these are then also linearly deducted from your utility. So if you pay an amount B, then your utility goes down by exactly that amount. This is a standard assumption, but it is by no means an innocent assumption. So one of the drastic consequences of this is what is called no wealth effect. And that means that if I would give you 100 euros, then it does not matter how much money you already have. So if you would be broke, then the increase in your utility from that 100 euros is supposed to be exactly the same as when you would already be a millionaire. And that's of course a very strong assumption, right? So usually that's not how individual humans evaluate money. But in certain contexts, like when you talk about the firms or companies, this might well be a reasonable reflection of how they think. So you should think of the applications of this type of model in that context. So don't apply it in psychology, I would say. Okay, so this is the setting. We now know what our problem is. We have a very general economic setting, and we want to achieve efficiency in the sense that we want to find an allocation that maximizes total utility. And we assume that agents have a valuation function for allocations, together with the assumption that money enters the utility linearly. In that setting, we can build an auction that has the property that, well, first of all, bidding truthfully, so reporting your true valuation, is going to be a dominant strategy. So it's a dominant strategy to always report the truth. And secondly, of course, if people do that, then the resulting allocation is going to be efficient. And that's called the VCG mechanism, so Vickrey, Clark, and Groves. And as any auction mechanism, VCG consists of three parts, namely strategies, allocation, and payments. And so first we have to say what the strategies are. So what can you do in this auction game? And then after that, based on the strategies that players took, you have to decide on how you're going to allocate and what each agent is going to pay. But let's start with the strategies. Strategies are relatively simple, at least are simple to describe. It's a one-shot, so VCG is a one-shot auction mechanism. So people report, well, what they're going to report is a valuation function, and they do that independently of each other. So they don't know what the others are reporting. They simply once and for all communicate their own report. And then the auctioneer collects all these reports and then goes on with the second phase of the auction. But in the first phase, agents simply report a valuation function, meaning a reported RI that assigns to each allocation a real number. That does not need, he does not need to report the truth, of course. So VI is one of these that you could possibly report, but you are allowed, or well, allowed, at least nobody can prevent you from reporting falsely, because nobody knows what your valuation really is except you yourself. So there's nobody who can actually check whether you report the truth or not. So. But these reports are made simultaneously. So in that sense, this is a one-shot game. In other words, a sealed bid auction. So you simply write down your valuation function for each allocation. You write down how you value it. You put all these valuations in a sealed envelope and you hand it over to the auctioneer. Based on all these reports, the auctioneer then decides on two things, like I already said, allocation and payment. And the allocation is fairly simple. So we don't know the VIs. And what we want to do is maximize the total valuation or total utility, the sum of the VIs. Unfortunately, we can't do that because we don't know the VIs. So what we do instead is the second best thing. We are going to maximize total reported evaluation. So we're simply very naively act as if everybody reported truthfully. And so we take the RIs that are reported as the truth, and we use those to then find a total utility maximizer. So we select an allocation B star with the property that the sum over all the reported valuations is maximized by that B star. So the sum over the RI B stars is largely equal to the sum over RI B for any other B in A. So like I said, B star is a maximizer of total reported valuations. Good. So that's that. So far, well, of course, it was a bit of notation, but we haven't done anything dramatic yet, right? So we just said that people can report valuation functions. They simply have to answer the question, what is your valuation function? And then even though we know that they may lie about that, we act as if they reported the truth, and very naively we maximize the reported total utility. So and how are we now going to prevent that agents report untruthfully? Well, that is done in the payments, and that is the clever part of this construction. So how does that work? Well, as follows. You're going to look at an agent I, and we're going to compute the payment for that specific agent. And what does he have to pay? Well, he has to pay what is called his externality. How is it computed? Well, we first act as if agent I was not there. Okay, so just imagine that he is not present. All the other agents are present except agent I. What you can do then is to look at those allocations that maximize the total reported valuation of all the other remaining agents. So that is the BI double star. So what it maximizes is, as you can see here, so for each J other than this agent I that we chose, right? So this is agent I. We are going to compute the sum of reported valuations of this BI star star. So that means that if this allocation is chosen, then the sum of reported valuations over all agents other than I is maximized, right? This is larger or equal to any other sum that we can form for any other B in A. And what is agent I now going to pay? Well, he's going to pay the difference between that amount and the amount that the other agents currently have under the B star that we actually chose, the one that maximizes all the reported valuations. So why is this called an externality? Well, you see what is over here is the current total utility of, let's say, all agents J other than I under, well, the total utility maximizer. But this here is the same, but then under this BI star star, which is when you would not be present. So this is really maximizing, the value for the other ones. And this here might actually be less. What does it mean? It means that, you know, if I would have a bar of chocolate, then I could give it to someone who really, really likes it. But of course, the downside of that is that if that person would not be there, that somebody else would get it. So you see, for the other ones, it's always, there's always a price if one more person joins, because you have to share it with more people. So in total, of course, the utility goes up. but for the people who were already there, so this newcomer is actually bad news, because he might take in some of the goods that are now assigned to this newcomer. And that's what this is counting. So the decrease in total welfare of the other agents due to your presence. That's what this is. And that is what you have to pay. And each agent does that. So it's known as the externality. And if we do that, then we have the following result, that under this payment, what we're going to prove is that truthful reporting is indeed a dominant strategy. And a consequence of that is that if people then actually do that, that we're going to have that we have maximized welfare. But in order to get that theorem, we need a little bit of notation and game theory lingo. So what we're going to say is that, so this is, you could say, the domain. We're going to look at all valuation functions from A to R, and we call that DI. Just all the functions that you can make on A. And what's now a strategy? A strategy is a function that assigns to each such an object, so a valuation function, right? A reported valuation function. So to each element in TI, it assigns an element in TI. So there's a true valuation VI, and then you have to decide on which reported valuation you're going to make. What is a dominant strategy in this context? So a dominant strategy is now a strategy of this type. So it's a strategy, and it's a dominant if, well, so given any report of other people, this strategy maximizes your welfare. So you have a valuation for yourself and a profile of reported valuations of the other ones, and this is going to maximize your utility, so the report. That's a dominant strategy. And the theorem is now that under the VCG, reporting the truth, so if your valuation is VI, then reporting VI, that is going to be a dominant strategy in this sense. So it maximizes your utility, given the reports of the other ones. And so this is one thing. Of course, this is nice, but this is, you could say, only a means to a goal. As economists, we are not necessarily interested in the truth. What we are interested in is efficiency. But of course, if people report the truth, then in this mechanism, automatically, as a consequence of that, the allocation is efficient, because we maximize reported, total reported valuation. And if people report the truth, then that means that it's equivalent to maximizing the true total valuation. So this is the theorem, and I'm going to talk about the proof in the next video. So I'll stop here, and I'll see you in the next recording.